Okay, let's get started. We have a few people online. Thank goodness the internet. I got the internet working today, so get them on board. So today I want to go through a numerical example of CLT. So basically the same theory we went through a few times. Then the same few slides. I'll just quite quickly fly through the key assumptions, the coordinate system, the code, layup codes, layup properties, motion, strain, stress, loading. This is a stress external load. This is equilibrium. This is stress-strain relationship. We went through all these. This is a relationship between strain and the loading. And similarly, and then the integration to get ABD matrix. And this is AB matrix, and then BD matrix over here. BD is over here. All right. So these are physical meanings of these matrices. And this is when you put all everything together. So what I'm going to do today is basically go through an example here. We went through these steps, abstract terms. I want to basically solve a problem, very simple laminates. I'll go over there. I'll flip back and forth. I want to first review the problems. This is the problem we're going to solve. So we're going to go through the steps to solve this problem. Go through the whatever A steps. This is the laminate, 3-layer laminate, graphite epoxy. There's a load. This is a biaxial tension. It's pulled both directions. Same load. All right. Using the unidirectional property of graphite epoxy, assume each lamina, each layer has a thickness 5 millimeters. This is not realistic. This is just for education purposes. Usually they're not as thick as that. So part A is find the matrices A, B, and D for the 3-ply lamina, and then calculate mid-plane strain curvatures, and then calculate global and local stresses on top surface 30-degree plies, which is the first one. Top surface of 30. So it's basically top surface 30 plies, this interface right here. That's a top surface 30-degree plies. Percentage of load taken by each ply. So we can calculate. Once we know stress, we can integrate and figure out which layer take more stresses. Those are basically flow down. All right. Back to the, there's a diagram. We use this diagram. This is the one we explained last time in the last lecture. So there are several steps. These are steps starting from 1 to 10. So so first step is construct reduced stiffness matrix Q for each ply. In this case, we have 3 plies. So we have 3 Qs, 3 plies, right? Actually, there's only 1 ply because they're the same, right? So you have 1 Q for, you only have 1 Q in this one. You have different Qs if you have different materials, right? If the same thickness, same material, it's the same Q. They're calculated using the engineering properties, E1, E2, nu1, 2, and G1, 2. All right. So for all the calculation purposes, we're going to use the data from this table. I'll upload the slides online so you can have this. For the homework and everything, we're going to use this set of data. So this basically tells you the typical lamina stiffness for 3 different laminas: graphite epoxy, gloss epoxy, and boron epoxy. In this case, it's graphite epoxy, so we have this properties here. So we know it's E1, 26. This is the English unit. The unit is MSI, million PSI, right here. M is 10 to the 6. K is 10 to the 3, M 10 to the 6. So we also know E2. E2 is modulus perpendicular to the fiber, and then nu1, 2 is Poisson ratio. Now, what is nu2, 1? How do we calculate nu2, 1? Now, there's a relationship. Nu1, 2 and nu2, 1 is related. if given one, you can always calculate the other one. Doesn't matter which one. They're related. Like if nu1, 2, E1, E2, you can calculate nu2, 1 with this relationship, right? It's pretty straightforward. All right, why do we need a nu2, 1? Because we need a nu2, 1 to calculate a Q matrix. See, nu1, 2 times nu2, 1 minus E1 divided by that. That's Q11. You calculate Q11, Q12. What about Q13? What is Q13? Or Q16? Some people call Q16. What is that number? It's 0. Remember, for the reduced stiffness matrix, for isotropic material or transverse isotropic, your Q matrix only has first 4 corners non-zero, and then the lower corners is non-zero, then the other 4 are 0. So those are 0. So these are all your non-zero entries. So Q11, Q12, what about the Q21? What is the Q21? Q21 is same as Q12. And then Q22 is that number, and Q66 is the lower right corner of that matrix, and the rest of the entry are 0 in that matrix. That's your Q matrix. We call it a reduced stiffness matrix. This is in the material coordinates. 1 and 2 are material direction. 1 is fiber, 2 is transverse. Okay. Any questions? I assume now you can calculate Q, right? Pretty straightforward. You just read off the material property from the table, E1, E2, and you figure out nu1, 2, nu2, is. G12 is also given. G12 is here. G12. This is G12. This number right here. 1.04 million PSI. That's G12. Okay. So for your convenience, I'm also provided this table. This table is everything in that table, but everything converted to SI units. You can do that on your own, but this is already converted for you. So this is a E1 is 181 gigapascal. E2 is 10.3 gigapascal. G12 is 7.17 gigapascal. Okay, so I'll give it to you. All right. So depends on the units of the given condition. You can choose to using English units or US customer units or SI units, whatever more convenient. If most dimension given in inches and pounds, I would choose PSI. If other dimensions given in millimeter newtons, I would choose SI. It's just more convenient that way, right? Okay, so the first step. Back to the first step. First step is construct this matrix Q, this 3x3 matrix. You calculate each entry using these numbers. You have to make sure you use the right material. You pick the right material, whatever the problem described. If it's glass fiber epoxy, use the glass fiber epoxy properties. Carbon graphite, carbon epoxy, use the carbon epoxy. Now, second step is transform the stiffness matrix into the global coordinates. They're called Q bar. Q goes to Q bar for each ply. Now, how many Q bar do we need to calculate for this problem? So we have 3 plies, we do 3 Q bars. Each ply has different angles, right? We have a, what is it, 0, 0, 30, 45, right? So you got to calculate 3 matrices from the Q, transform Q into 3 directions. All right, so how do we do it? We transform using this set equation. This is extracted from a previous slide. You had this in other slides, but I just put it all together. So they're sort of close. You can. So you have the entries in the Q matrix. You plot the Q matrices, the elements in the Q matrix. You can calculate Q bar. This usually is a full matrix. It's a symmetric of a full matrix. So you have 6 numbers. You understand what C and S are? Everyone has. So what is S? Sine theta. What is C? What is theta? It depends on the plies, right? The plies are in the problem that we're talking about. There's 3 thetas, right? They're given here. So for the top ply, theta equals 0. For the second ply, theta equals 30 degrees. For the last ply, theta equals minus 45. You just calculate and plug and chug. A little bit tedious if you do it manually, but if you write a program, you write it once, you can use it forever. You write these together, you type it in MATLAB and once, and then you use it forever. You can debug and check. This is all the queues. Why it's not a 9 element? Why is it 6 element? 3 by 3 matrix. Why I calculate on 6 numbers? Symmetry. This matrix is symmetric. It's a symmetric with respect to diagonal. So it's only 6 independent. So Q12 is given here, not Q21, because Q21 is equal to Q12. They're the same. Okay, symmetric. Okay, once we got a Q bar matrix, and the next step, now we have 3 Q bar matrix for 3 different layers. All right, so and then knowing the thickness T for each ply, find the coordinates of the top and bottom surfaces. And then you, for each ply, you need to basically you lay out the coordinates for the thickness direction. You set up your Z equal to 0 at the middle, at the midplane, at the middle of the ply. So basically, this diagram is basically a rough idea. It's the idea how you do it. Let's say you have n plies. You sum all the thickness, you know the total thickness, that will be h in this case. And then you locate your midplane, half h from top, half h from bottom, right? That your z equals 0. Then you figure out the coordinate for each layers. You're going from the most negative. The most negative z is 1. Our z is going downwards. So the most negative, this layer will be the first layer, and then this coordinate is h0. And then h1, you just construct. You take h minus h plus 2 plus thickness 1. You got this h1 and so on and so forth. You can figure out all the h for each ply, right? It's like a layup. You lay up. In this case, very simple. It's 3 layers, same thickness. Each one has a 5 millimeters. It's very simple. If 100 layer, you mix different materials. You carbon graphite, glass. Each laminate a different thickness. It's the same approach. You just have more numbers. You can sit down and lay them out. Just figure out the coordinates of all the interfaces. Okay. So make sure that you between h0, h1 that you layer 1, h1, h2 layer 2, and so on and so forth. It'd be nice to set up a table in our MATLAB code, whatever it is. You need to first set it up. Okay. Now, why do we need this? Because we need this to calculate the ABD. The ABD, the scaling factor, is function of h. Remember, we scale Q bar by some sort of h function, and that get you A, B, and D, right? So we need to set it up before we go for A, B, and D matrix. Okay, let's set it up for our plies. Our ply has 3 layers. It's the piece of cake. That's how we set it up, right? You see this drawing is how you set it up. First layer 0, second layer 30, 45. So this coordinate is minus 7.5, minus 2.5, 2.5, and 7.5. This will be h0, h1. You can use number z, z0, z1, z2, z3, doesn't matter. You can pick your variables. Right? Any questions? Pretty straightforward. Okay, and then we have everything we needed to go for A, B, and D now. Now the next step is step 4. Okay, use the Q bar matrix from step 2 and the location of each ply from step 3 to find the 3 stiffness matrix A, B, and D. And I moved the formula here, so you can have the formula. This is the formula for A, B, and D. It looks pretty scary, but really it's just multiply the matrix by a scalar and then sum them up. So that's it basically. There's not rocket science. So you see A matrix is a sum of several Q bar matrices. Each Q bar is scaled by this factor. Now you recognize this factor? What is this factor? That turns out to be the thickness of each layer. The difference between H and the thickness, right? So you basically multiply thickness of each layer with the associated Q bar and sum everything up. How many matrix do we sum up in this case? We have 3, right? We have And they happen to multiply the same number 5 because the thickness is all equal. Okay. On the B matrix is a little more complicated. So your scaling factor is not a thickness anymore. It actually varies depending on where your plies are. Is hk squared minus k minus squared divided by 2. So this actually depending on where the location of the matrix is actually a different number, even though the same thickness, but this scaling factor differs depending on the location of the plies. And you got to calculate based on the layout, your H or Z numbers, right? And then the third one, similarly, is cubed, H cubed. Scaling factor is H cubed minus HK minus 1 cubed divided by 3. That's scaling factor for each matrices. Then you multiply each Q bar and sum them up. You got A, B, and D. They are 3 by 3 matrices, right? Each one of them is 3 by 3. Because Q bar is 3 by 3, doesn't matter how many you sum up. You add up, it will be 3 by 3. Okay, any questions here? And you notice that A, B, and D have different physical dimensions. This is a little different. Remember before when we write the equation, all the term you add plus or add minus everything, yeah, just something same units. The ABD matrix actually is a matrix of mixed units. The different entry, different element, different units, right? You can see here. So they multiply different. H has a unit dimension. So once you multiply that, it becomes different units. Now let's go to this problem that we had. So this is a Q matrices that you can calculate this. This actually is a good example if you want to do sort of a debug code. You can start writing your code, and you can challenge your code with this set of data. You compare results with this. This all has all the calculations in. Even though it's a very simple example, it's still you can use it to check your code. You can set up your code to solve for this minute. Okay, this is a Q matrix. For all the layers, they're the same layer. And then this is a Q bar. The Q bar matrix. Now I said the Q bar matrix is a full matrix. How come the first one has 0 entries? That's a 0 degree. That layer has no rotation because the 0 degree. The first layer is 0 degree. So the one direction actually is the same as the x direction. So that Q bar matrix doesn't change. It's the same as the Q matrix because it didn't rotate. 0 degree didn't change. So the first matrix is Q bar after coordinate rotation. You have a 0 degree coordinate rotation, so nothing changed. Same matrix. But the other two changed. You see, the other two is not a. It's not a doesn't have the 0 entry anymore. It's full matrix. Okay, symmetric but full matrix, right? Pay attention to the dimensions. The common factor. These are gigapascals. So actually showed up here. This is the giga part. 181 gigapascal. This is a giga, because every term is a gigapascal, so taken out. You don't have to write this for every term. You just pull the scaling factor out. So this is a 30 degree minus 45 degree. Okay. Now, do you know the difference between minus 45 and plus 45? Or do they? Is there any difference? Now, which one is plus, which one minus? Then, if you give you're given layup, which one you call plus, which one you call minus? No, I mean, that's a good answer. All right. Now here's the answer. This one. All right. If you stay, look at the definition here. This is definition of theta. If you look down along the z directions, the z is pointing out of the screen. It's a right-hand rule. X cross Y give you Z, right? If you look toward the arrow Z direction, the counterclock rotation of X is theta. Positive is counterclockwise. That's how you determine plus. That's how this series derived this way. So if you go this way, if you counterclock rotate, this fiber's counterclock rotation 45, that's plus 45. If you do clockwise rotation, is minus 45. Okay. So that's how you determine plus minus. You had to look along this direction and determine, is that fiber rotated counterclockwise or clockwise? All right. Now you can say this is a, if theta equal to 45, you can say it's a counterclock 45, but clockwise, what is that? You can rotate the other way, a bigger angle. 180 plus 90 plus 45. You can do that one as well. It gives you the same results. Doesn't matter if you do positive 45 or the negative of this angle, it gives you the same result. But obviously, this is more easy to calculate. Okay. So whether it's positive or negative depend on this setup. Okay. All right. Back to our problems. All right, now we got Q bar. Now ready to sum. Okay, this is manual sum. We first sum to get A. A is you multiply this Q bar with thickness for every layer, sum them up, right? So this is thickness is so thickness is basically 5 millimeter, right? You multiply 5 millimeter. You just multiply this HK minus K1. These are equal to 5, basically. 0.05 meter, basically. It's all the same. And you multiply, you sum, this is sum, and there's a sum here, and you end up having A matrix. This is all the number written out here. It's a 3-layer sum up. Escape. Now you got A matrix. Is that unit correct? It's Pascal meter. Does it make sense? Yeah, obviously, because each entry is for A matrix, each entry is a Q. Q is Pascal, and you multiply thickness, obviously Pascal meter, right? Okay, that's A matrix. Then when we do B matrix, you multiply a different scaling factor. It's H squared minus H squared. Square minus squared, and then there's a 1/2 here, gigapascal. First layer, and that's second layer, the third layer. All right. It turns out that for B matrix, the outer layer has a bigger contribution because this factor is higher for outer layers. This factor is higher. Okay. Now, what will be the unit for this? What will be the unit for this B matrix? What's the physical units? It's Pascal meter. Pascal meter squared. So it's Pascal meter squared right here. So this is B matrix. Once you sum everything together, you could possibly take some of the common factor out. For example, 10 to the 5 to here. That's fine too, depending how you want to write. Okay. One thing you want to check, they're all symmetric. If your A, B, or D, whatever you come out not symmetric, you did something wrong. Everything is symmetric. Why you can guarantee everything's symmetric? Because your Q bar is symmetric. So no matter how many symmetric you add it together, it'll stay symmetric. If you just look at your result, intermediate result, you find your A become unsymmetric, then you go back and check something went wrong. Okay. All right. Now the D matrix, similarly, your Q bar multiply different scaling factor. This scaling factor is length to the power 3 cubed. Okay. So this unit will be Pascal meter cubed, whatever you got. Okay. And you sum 3 together, and that's your D matrix. Okay. Pascal meter cubed. At this point, we are ready to do the ABD all together. We basically A, B, D. What is this matrix here? B, the same as B. Okay. Is this matrix symmetric or not symmetric? It's symmetric. Okay. All right. Let's back to our map. Our map says we are at step 5, I think. All right, so we just finished step 4, and then we got ABD, substitute made value finding ABD, apply force and moments. This is basically put ABD together with so what that means is this: you get ABD matrix figured out, and you figure out your loading matrix, and this is what you want to solve. This is a mid-plane strain. This is a curvature. Now, in our case, for this reply, what is the loading here? We have what is the left-hand side? What's the vector on the left-hand side? Remember, what does it have a loading? What was the other? All 0. There's no load. There's no shear, no bending, no twisting. All 0. Tension and X, tension and Y equal to 1,000 Newton per meter. You put 1,000 here, you put 1,000 here, and make the other 0. And then you have your governing equation. This is the governing equation to be solved. Now, how do you solve it? Many technique. You can use MATLAB, or in Excel, I invert that matrix and multiply it to the left-hand side. So I first calculate the inversion of ABD, and then I multiply that matrix with that vector here. And that give me this solution. So you're gonna have a solution which is sig numbers, which represent that unknowns. Okay. All right, so that's step number 6. Solve the governing equation to find the midplane strain and the curvatures. Okay. And then number 7, knowing the location of each ply, find the global strain in each ply. The global strain in each ply is related to the midplane strain and curvature and the location of the ply by this equation. This is the equation you want to use. This is a global strain in each ply. You have 2 normal strain and shear strain, which is related to the midplane strain plus curvature multiplied Z. Now, what is Z? Z is the location of the plies, right? Now, in our case, for ply 1, what is the Z for ply 1? So what's the Z for ply 1 in this case? This is ply 1. What is the Z for ply 1? It's not a single number. It's a range, right? It's from here to here. It could have a high strain over here on this face or low strain on this face, but it's a range. It depends on where you want to calculate strain. Okay, the average strain, you can take the average. But see, this question asks you global and local stress on top of surface of 30-degree ply. Now, what's the Z for that? Minus 2.5. Okay, so remember the strain varies in Z direction. Each layer has finite thickness. There's not a single Z. There's a range of Z's. You can find the stress. Usually people calculate the stress on top of the layer and the bottom layer, both. You calculate strain stress on both locations. Usually on one side is high. Usually if the bending, usually top and bottom face are high. You calculate strain here, stress here, strain here, stress here for this layer. And then you can make decision which side is high. And that's usually when you start to fail, they're from that side, okay? In this case, it's pretty simple. We plug in Z equal to minus 2.5 in that equation. Let's go see this steps. Our ABD here. All right, so it's governing equation. We solve, we found the solution. This is the solution. Okay. And then we plug in mid-plane strain Z multiply curvature. All right. Now the mid-plane strain is just the first three numbers here. This first three number is a mid-plane strain. And Z is minus 2.5 millimeters, minus 0.0025 meter. We use meter, right? SI units. And that's the curvature. You multiply some together. And this is the strain at this interface right here. That's a strain. Okay. Now strain typically it's a very small number. Whatever strain you calculate in your code, just make sure it's usually very small. It's like a ppm level. It's very small. Okay. All right. And you can calculate strain anywhere. What if I want to calculate the strain in the middle of the 0 degree? What Z you put it in here? In the center of that top layer. Is the minus what? What I want to calculate strain right in the center of this layer? What Z you put in there? Yeah, minus 5 is the average of the top one. Yeah. If I ask you to calculate the strain on the top of the ply, then you put minus 7.5 here, right? The bottom ply is 7.5, positive 7.5 at the bottom ply. Yeah, pretty straightforward. Okay. All right, and then back to our maps. What can you do is next thing is calculate stress, I believe. All right. So knowing the location of each ply, find a global strain each ply. Yeah. To find a global stress, use a stress strain relationship. The global stress and global strain are related by a Q bar matrix. You already have them. You can directly, if you figure out the strain in that layer, you can directly multiply strain by the Q bar, you get a stress in the global coordinates. That means XY coordinates. Okay. So the Q bar matrix are these matrix. All right. So we had 3 of those for each layers. All right. This is each layer. If you know this is layer number 2, this is a Q bar for it. You multiply this Q bar by the strain you calculate the strain number. You stress multiply a vector, you got another vector which will be the stress vector. Be sigma x, sigma y, tau xy for that layer. Okay. All right, and then we always want to know the stress in the material coordinates. It's just more intuitive. People like those stress. You find later that that stress give you more insights. We eventually want to find the stress in even in the xy coordinates is give you the global stress, but you always find how much stress is along the fiber direction. This problem didn't ask for it, but I want to point out how do you go back to the local coordinates. You do the transformation like this. Okay. So the relationship between the global stress and global strain is through this Q bar matrix, and you can transform your global strain to local strain through this matrix. Okay. T and R are given here. Again, C is cosine theta as the sine theta. Theta is the angle we talk about in the coordinates layout. It's a counter clock rotation from X to the fiber direction. Okay. All right, so you can construct this 3, you can multiply this 3 together like this, and you get a matrix. You multiply this matrix with this global strain, you got local strain for that layer. You can transform back. Now, once you got a local strain, how do you get local stress? I mean, the material direction stress. You just multiply together, right? This is a, oh no, you just multiply Q. You multiply Q matrix with this E1, E2, gamma 1, 2, you got sigma 1, sigma 2, tau 1, 2. right? So that's how you go back to the material coordinates. Now this problem actually didn't ask for that. This problem just asked you to calculate a simple stress on top of the 30-degree ply at this location. You calculate strain first and you multiply Q bar. That's it. And then the second part is the last part of the question is percentage load taken by each ply. All right. So we know Nx is sum of the stress sigma x over all layers. You integrate from top to bottom sigma x, you get Nx. But if you integrate from here to here instead of all the way down, you can integrate from here to here, from minus 7.5 to minus 2.5. And that will be the accurate x direction load taken by layer 1. And you can integrate sigma x from minus 2.5 to 2.5. That will be the x direction load taken by layer number 2. You can do this integration different intervals. That give you the load taken by each layers. Okay. Then you know how the load is partitioned, which layer taking more load in this design. Okay. So let's see how that's calculated. ABD and solution stress. All right. So we basically, in this case, we calculate the global strain in each layers. Each layer, remember, you can calculate the strain. The strain is not a single number. It has a finite thickness. So in this case, what's calculated is what's on the top layer, what's at the bottom layer, what's in the middle. All right. For each layer, top, bottom, middle. You see 3 rows. By plugging different z's, you get different rows. Okay. And then the stress is basically strain multiplied by this Q bar matrix for each layers. And you can calculate stress on the top of the ply, middle of the ply, and bottom of the ply. You can calculate 3 for each ply. Okay. All right. And then you can integrate. Basically, you local stress strain. This is basically the question is about portion load by taking each plies. You integrate. You integrate your sigma x from here to there, which is really is sigma x. Whoops. This is your sigma x. That's your sigma x. You basically integrate sigma x from top to the bottom of this layer. That's the nx taken by this layer. Okay. I think it's linearly distributed. You can use the average multiplied thickness. That will be the same number. You can do integration, but it turned out to be the average multiplied thickness. Okay. Same thing here. The x directional load taken by this layer is this variable integrated over the thickness from top to bottom this ply. For third ply is this integration sigma x over the ply. Okay. Similarly, you can figure out the y direction load, the tensile in y direction, how much is partitioned different plies. You basically integrate this column over the thickness of each ply. This will be your shear. Okay. Now, if you do that, and then it turns out that these are equal to this. First ply taken this much load, second ply this much, third ply that much, x directional load. The sum total of the load shared by each ply is you just calculate the percentage. Okay. All right. This, and this. All right. Any questions? This is a very simple example. Of using CLT to do some calculation of stress strain in the laminate. All right, so we basically went through the steps. Right here, we went through these. And you can start writing your code pieces at one piece at a time. Now, you don't want to wait for the. You can start writing, and then you can check against examples here. I have more examples. I can give you a case to check. So you write your code. I'll give you certain calculations. You check your number with my number. If 3-4 cases match, typically is correct. This will be all correct later on. All right. Let's see. These are the. All right. You can calculate. You can rearrange this matrix. This is a. You can rearrange. Once you got ABD matrix, you can do all kinds of things. Okay. You can manipulate the ABD matrix to come up with a number that characterize the how stiff the plate is under bending. We call it flexure modulus. You can come up with this number. You can sort of get a metric that indicate when you bend the plate how stiff it is. So here's the steps. So you basically partition the matrix into these elements, block matrix. So you have A block, B block, B block, D block, and then you call this subvector. This is a 3x1 vector. You call it tension. This is actually tension and shear. Tension, tension, this is shear. So this is load. And you call this bending. This is actually bending, bending, and twist. This one's twist. Okay. So, but anyway, you name this 3 N and name this 3 M. And then you name this epsilon. You name this kappa. So this is a stretching midplane. This is a curvature. You rearrange this. You just think about, you just regard this as a single number. This is a single element. This is a single number, a single number. You can do this. You can actually, you can invert it. You can invert it to get the A star, B star, C star, D star is the inversion ABD matrix. And then it can be proved that C star is the transpose of B star. Okay. So this this A star, B star, and D star matrix are called extensional compliance matrix. The invertive stiffness matrix are compliance matrix. All right, so they basically characterize the compliance in the stretching mode, A star, and in bending mode, D star. And this is the coupling between, B is a coupling matrix between them, between bending and stretching. Okay. Oops. All right, this is the compliance form. You can call some of the terms as the modulus of the laminate. For example, this A11 is a metric of how stiff the plate is. Everything lumped together, the whole plate with many layers against tension loading. This how stiff it is against tension with A11. Okay. And then you can define some equivalent engineering properties. You imagine you're doing a test with certain loading. You just base this is uniaxial tension. Imagine you put a uniaxial tension in the plate. Only non-zero load is stretching x direction load. the other is 0. If you run that test, you find that your strain in that direction is this multiplied by this. You just exercise this math. So you can basically call this number, you take the sigma x divided by epsilon 0x. Sigma x is your stress, is the nx divided by h divided by this number here. And you got a 1 over h times A11 star. And this number is the equivalent of a Young's modulus of the plate of this laminate. So why sigma x equal to nx divided by h? What is h? H is the total thickness. Why sigma x is nx divided by h? What is nx? Nx is linear low density. It's Newton per how wide the plate is. Now, if you take the Newton divided how wide per plate is and then how thick the plate is, that will be average stress. Is wide thickness is area, right? So you take nx divided by thickness, which is h, that gives you the total load divided by the total area, which is average stress, right? That's average stress, nx divided by h, right? And this is your strain in one direction. You take average stress divided by strain, and this ratio is what commonly known as Young's modulus. This is the modulus you get when you do an isotropic material. You pull it, the slope, okay. But composites usually behave much more complicated. Usually they have other strains. They may twist a little bit. All the couplings exist. But if you just focus on the stretching along the loading direction, this quantify how stiff this plate is. Okay, give you a single number is a metric of how. And the true stretch each layer is not this sigma x is just an average stress. It's not a true stretch in each layer. Remember, the stress in each layer is not equal. They have certain partitions, right? We actually just figure out the partition between them in part D of that problem. You had to figure out which part. This sigma is an average stress. Okay. So we call this the engineering constant of a laminate. Laminate is a collection of lamina. Lamina is layer. So this metric quantify the x direction stiffness of the whole thing. Okay. It's engineering properties. Similarly, you can calculate other things. You can calculate EY. EY is you also, if you do imaginary experiments, you apply tension in y direction only, no shear, no x load, and you calculate the y direction strain that equal to this. And then you can calculate the equivalent Young's modulus. Again, this is your average stress. You calculate the equivalent Young's modulus equal to this. Okay. And you can do shear modulus. The equivalent shear modulus of the laminate. It's a very similar case. You again imagine there's a test done this way. You apply shear load, and that's a shear strain, and then the ratio of them is the shearing modulus. And you can imagine doing a bending test. What is it? The bending test. You can imagine this is when you do a bending test. Imagine there are no tension. All the n are 0. You're actually doing bending tests. You have like only bending in x direction. There are no bending in y direction, no twist. And you can calculate the curvature in x direction. And that will be the curvature x direction. Then you can calculate, you assume this is a beam. You assume there's a beam, isotropic material, have that bending stiffness. You can calculate the equivalent modulus using the curvature and the moment, the ratio. This is based on beam theory, fundamental basic beam theory. So this is the number you come up with. This number, depending on D11, tell you how stiff this plate is if it bend in x direction. Okay, it's a metric. And you can calculate other things. This little f means flexure. Flexure means bending. That means the modulus, equivalent modulus under flexure mode. Okay. And x means you're bending, the moment is in x direction. Okay. You also have moment in y direction. Okay. You can also have a twisting. You can apply a twist. You can calculate the equivalent shearing modulus, flexure shearing modulus, using the D matrix as well. Okay. All right. So we can actually calculate these using the example we just did. All we need to do is invert. You see, this number depends on a single entry in the inverse ABD matrix. You see, this entry depends on H and D22 star. This entry depends on D6 star and H. And this depending on D11 star. So once you have the inverse of ABD, you have all these numbers. You just pick them out and then calculate like this. And then your see this all the G, X, Y all depending on A matrix. So and then EY depending on A22 and H. EX depending on A1 and H, right? So you basically invert ABD. You get inversion, and you get these matrix. You get these numbers calculated, and you get a D, and then you calculate the inverse of D. This is D11 star, D22 star, D12 star. You get these parameters like that. All right. Any questions? Where's the classification of matrix? I guess I didn't put it in here. So ABD shows some certain pattern depending on the matrix is symmetric or anti-symmetric and balanced and unbalanced. I guess I didn't have it here. I'll talk next time. Now I want to talk about another subject, which is thermally induced stress. Thermally induced stress. So, which is interesting subject because you know the different layers due to their layup. If you subject the material to some temperature change, they all want to expand a different amount in different directions. Now by now you should have an idea how each lamina want to expand. Now each lamina expand much less in the fiber direction, right? Because fiber doesn't expand as much as polymer. The matrix want to expand. If you think about it, if fiber running this direction, matrix running this direction, if you give a temperature change, which part can go fatter? That direction. This direction is really constrained by the fiber, right? And then if you orientate this lamina this way, this lamina want to expand this way very much. And different layer auto expand different amounts. They actually fight. This is called a thermal stress. The reason they have stress, you don't even need to load it. You just change the temperature. There usually is a something called a zero stress temperature, which is close to the curing temperature. So when you cure the matrix, everything all the layer together in the autoclave, that's when there's absolutely no stress between all layers. Now once it start polymerize, form each layers, and that state, they start to build stress. So when you take the laminate out of the autoclave, they're already stress in there. The layers already start fighting. Okay, but an interesting factor is, since you have no external load, all the internal stress actually balanced, self-balanced. They fight, but they somehow balance out. You know, if two layers are fighting, the stress you're pulling on me and me pulling on you is always equal, right? It doesn't matter how many layers. Once you slop them together, they'll find a balance. Okay, we can figure out what that stress is by doing this kind of thermal analysis. Okay, so this is a fundamental equation to enable that analysis. So we are partition the strains. This is the total strain. The total strain. We think the total strain is a sum of the strain caused by mechanical loading and the temperature change. Now, if you move the second term ET to left-hand side, you know, you have a epsilon x, epsilon y, gamma x are equal to this m terms plus t terms. The m term is the strain due to loading. The t term is strain due to temperature change. So the only thing we says here, the total strain is a sum of these two effects, right? Okay, and we can further assume the temperature induced strain is a function of temperature. This temperature induced strain is a function of temperature. Is thermal expansion coefficient multiply a delta T. And the thermal expansion coefficient could be different in different directions, right? Could be, so X direction, Y direction, and then this is shear could be all different, okay? So this is a fundamental assumption we put in. We assume the mechanical and thermal strain are additive. They together give you the mechanical strain, okay? All right, we assume the hygrothermal stress is basically, if you connect this laminate together without bonding them, without glue them together, each one can freely expand to the zero stress state, then there's no mechanical stress. The fact that there isn't mechanical stress, even though you don't have external loading, is due to the fact they fight. Okay, so there will be mechanical stress, and then the mechanical stress is related to the mechanical strain through this same matrices. So we argue that what causes when you have a mechanical strain, there will be mechanical stress. They're related by the same stiffness matrix. Right, that makes sense? All right, so this actually occurs at every layer. Every layer there's a, this is a thermally induced stress, is this Q matrix multiplied the mechanical strain due to the thermal effect. Okay. And then you can basically figure out the total stress due to these mechanical stress induced by thermal effect. You can sum up throughout through the thickness. Okay. So the fact that there is no external load, these thermally induced stress must add up to zero. Each layer have stress, but they must be self-equilibrium. So this condition should hold. That means all the thermally induced stress, the resultant force from these stresses should be zero. This is basically says if your different layer, your fights, you should guarantee that you have zero sum. Okay. All right, then you can integrate. This is similar to calculate the A matrix. Oh no, this is similar to calculate derivation A matrix. You basically you sum. This is the same as this. We just plug in the QE matrix into them, and you have this. All right, Q multiply epsilon, or this is epsilon m. Epsilon m is the difference. Epsilon m is the difference between the total strain and the thermal strain. Okay. All right. And then, so all these equations we were looking at so far is basically the zero sum condition. We just plug in different relationships. What happened is you can argue the total strain. The total strain of the laminate follows the Kirchhoff assumption. The total strain. This is a Kirchhoff assumption. The assumption we use to do the classical laminate theory. And you keep going, you plug a Kirchhoff assumption in there. You can calculate, you can, the same you can transform to this. Okay. And then you sum. All right. You basically multiply Q into them and take the epsilon 0 kappa out. Okay. All right. And the A and B matrix are similar to the AB matrix we got before. It's basically same mathematical form. And then on the right-hand side is the NT vector. NT vector equal to this. Okay. And you get you can similar sum. You can similar argue that for the laminate, you should have a zero moment, because even though the laminate tend to curve, tend to bend, due to the fact that different layer fights against each other, your total resultant moment from all the layers together should be zero. You can figure out the total moment, and then you basically argue that the total moment is zero, similar to this this argument here. This integration zero. If you integrate of the Q, multiply Z times this, that's the moment that equals zero, which give you this equation here, the B and D matrix. Okay, and you can put them all together. Again, the M matrix is sort of equivalent to thermal load. It's like the equivalent loading due to the temperature change. Okay. All right. So at the end of the day, when you do this, when you calculate A, B, and D, the ABD is the same ABD as you did before, and you end up having a thermally equivalent load in plane and bending. These are calculated by Q bar multiply your thermal expansion coefficients for each layers. Okay. And then you can solve this equation. This, you can obtain the epsilon 0 and kappa, which will be the thermally induced warping or stretching of the laminate. All right, so if you have a temperature change of certain values, delta T, if given delta T, if you know the thermal expansion coefficient for every layer in all directions, you calculate these two vectors, plug in here, you solve the equation. This is how much the plate will warp. The first number tell you how much of the stretch. The next three number, the kappa, is how much it'll bend. It will bend. It depends on the layup. Some bend more than the other. It could warp really badly. If your thing's not balanced. One of the reasons the symmetric laminate are used more frequent than others. They warp much less. Everything is symmetric. If you're unsymmetric, it'll warp really badly. It'll be surprisingly high because the polymer really thermal expansion coefficient of polymer really, really high. You're talking about 60, 100. So if you cure at 200 C, 300 C, 400 C, you cure down room temperature, it'll warp like crazy. Okay. It heavily depends on layup. Now you can experiment numerically. You put a layup together, you calculate these. These predict how much it'll warp, how much the stretching plane, how much it'll warp. Okay. But this is the procedures to allow you to estimate for a given layup what will happen due to thermal effect. All right, so once you have the code, you see that the calculation is very similar to ABD calculation for internal stress effect. The only difference is you calculate this 6x1 vector using these equations. These are not the true load. These are the hypothetical load due to thermal effect. These are not the true load. You don't apply this load. Okay. These came out of the derivation. The reason we have this is the condition. The condition we apply to get this is the 0 moment and 0 force condition. Because we take the panel out, we didn't apply any force, any moment. The total mode is 0. Okay. All right. Any questions? Okay. I want to stop here today. I basically, I think I covered enough. Well, starting next week, so try to finish your homework by the end of this week, which is micromechanics. And then starting next week, we'll be I will assign a homework on CLT calculation. You should get your CLT code more or less ready by the end of next week. So you can start doing this week. Then we'll start by calculating a few standard cases. We'll check notes. You write your code. I have my code. I calculate a set of laminate with every result in every step, and you check again your code. So we benchmark against each other, and then we'll do numerical experiment with your code. The different layups, symmetric, anti-symmetric, quasi-isotropic, cross-fly, all those things. We'll see what kind of ABD they'll come out with, what is thermal effect, how they will work, and everything. Okay. All right. Any questions? All right. I'll see you guys next week. Good weekend. Yeah. You don't need. The rule mixer works beautifully. Yeah. People don't use it for that. Yeah. Transverse thermal expansion is it's alpha 2. It is one of the equations in the I'll follow up. You can see. All right, micromechanics. All right. Now take a look here. This is the equation you want to use. Yeah. New one too is you calculate from this equation. Oh, I see what your question is. So there are two numbers. Let's see. Oh, okay. I had to think about this. Which one is correct? Let's look at the derivations. That's right. There are two of those. I guess you need a new one two as a fiber and new one two as a matrix. Yeah, so it should be the same as this. This is there's no difference. This should be the same. This should be also a new one too.
Okay.
I think this is not the new tool one.